Today we'll be covering a lecture on diversity techniques in cellular system. The learning outcome from this lecture will be you will be able to understand the techniques to overcome the effect of fading, what are the various types of diversity technique, what is space diversity, what is selection diversity, and lastly we'll be covering a derivation of selection diversity improvement. So first, techniques to overcome the effect of fading. As we have seen in the last lecture that with fading, there are multiple copies received at the receiver, due to which there is an amplitude fluctuation as well as phase fluctuation at the receiver. So, which is a noise in wireless communication. So, to overcome this, there are three different techniques which can be used jointly or independently to overcome the effect of fading. First is diversity technique. It is a signal processing technique and it is used to compensate the multiple channel fading and increases the signal to noise ratio at the receiver. In wireless communication, there is no fixed path between the transmitter and receiver. So multiple copies of the transmitted signal receive at the receiver. So these multiple copies can be utilized at the receiver. They can be combined together to generate a signal at the receiver, and that signal will have a much better signal to noise ratio as compared to a single copy. So diversity can be done in terms of space, time, and frequency. Another technique is equalization. It is just like a filter which is applied at the front end of the receiver. The idea of equalizer is to recover a transmitted signal to the desired receiver. So to overcome the intersymbol interference, which arises due to multiple fading. Intersymbol interference means when the symbol of one receiver is overlapping on the symbol of another receiver. So this can be overcome with the help of equalizer. Third is channel coding. So when we transmitted a signal through channel, there is a possibility that at the receiver, the received signal is different from the transmitted signal. So to detect the error during the transmission as well as to correct the error, there are a few bits that has to be added to the transmitted signal. And these bits are the channel bits. So this can be used to improve the performance of received signal under the deepest fading conditions. Next is the types of diversity techniques. It is broadly classified into two types. First is microscopic diversity and second one is macroscopic diversity. Microscopic diversity is used to compensate for the fading that occurs at small scale, that is small scale fade, which is basically the fluctuation of the signal. Macroscopic diversity technique is adopted for large scale fading, to compensate for large scale fading that arises due to the variation in the terrain as well as the surrounding object. So we'll be covering the types of microscopic diversity that is to compensate for small scale fading. It is further classified into three types: space diversity, time diversity, and frequency diversity. So first let us see what is space diversity. So if for multiple receiver are separated in terms of space, then that is known as space diversity. So the idea of space diversity is that all these different channels have experienced the independent fading conditions. So for that we have a multiple antenna at the receiver which is separated from each other in terms of space. So the combination of all these multiple channels enhances the signal to noise ratio at the receiver, which is better than the signal to noise ratio of the received signal when we are not adopting any diversity. This space diversity is further classified into three different types. One is selection diversity, second is maximal ratio combining diversity, and third is equal gain combining diversity. So first is selection diversity. It is a type of space diversity. So in this, if let us consider there are m independent Rayleigh fading channels. Rayleigh means the distribution. In small scale fading, all these channels will experience a fading in terms of Rayleigh distribution. So, but all these channels will experience a different kind of fades as they are independent of each other. So we have m different antennas to receive all these different multiple channels, and these are m multiple gains, variable gains attached to each and every individual channel. So selection diversity will do what? It will select the strongest among all and give it to the receiver. So all these different channels are known as diversity branch. So let us see what will be the improvement when we adopt a selection diversity technique. So for that, let us see this derivation. If let us consider EB is the average signal energy, N naught is the noise power spectral density, and alpha naught is the Rayleigh fading distribution variable which is attached with each and every fading channel. So for each branch we are assuming that the average signal to noise ratio is given by this mean. So that is EB by N naught, signal to noise ratio, multiplied by the Rayleigh distribution variable. So the instantaneous signal to noise ratio on each branch is given by the instantaneous signal power per branch divided by the mean noise power per branch. So according to the Rayleigh fading distribution, the probability density function for each channel is given by this particular formula, where this gamma is the mean signal to noise ratio of each branch. So first of all, see the probability that each branch has a signal to noise ratio less than some threshold value. So the probability that each branch has signal to noise ratio less than the threshold is given by PR threshold I less than equals to threshold. So we integrate it from 0 to threshold, the probability P threshold I, D threshold I. So this will give us 1 minus exponent minus threshold I by gamma. So if we adopt the selection diversity of m different branches, then what will be the probability that all these m independent diversity branches will receive the signal less than the threshold? So that will be given by PR threshold 1, threshold 2, threshold m less than equals to threshold. So all these probability will be multiplied. So we'll get 1 minus exponent minus threshold by mean to power m. So this is the probability that all these branches of uh, selection diversity will receive the signal with the signal to noise ratio less than the threshold value. So, but we need the signal to noise ratio should be greater than the threshold value. So the probability that signal to noise ratio should be greater than threshold for one or more branches is given by PR threshold I greater than equals to threshold. So that means 1 minus the probability that all the branches will be getting the signal to noise ratio less than threshold. So that is 1 minus exponent minus threshold by mean to the power m. So this is the probability of exceeding a threshold when the selection diversity is used. So to find the improvement after adopting selection diversity, we need to determine the average signal to noise ratio of the received signal when selection diversity is used over the average signal to noise ratio when we have not adopted signal selection diversity. So to do this, first step is to find the probability density function of fading channel. So for finding the probability density function of the fading each and every channel is done by using a cumulative distribution functions. Cumulative distribution function and PDF are related by the relation that PDF is the derivative of cumulative distribution function. So the probability of the fading channel small pm threshold is given by the derivative of the capital PM threshold divided by D threshold. So by doing this, we'll get m by mean bracket 1 minus exponent minus threshold by mean to the power m minus 1 exponent minus threshold by mean. So to find the average signal to noise ratio for the received signal when the selection diversity is used, to find this mean, the formula is x fx dx. So the mean is given by 0 to infinite, x here is the threshold, and fx here is small pm threshold, d threshold. So by doing this, we'll get the average signal to noise ratio of the received signal when selection diversity is adopted. So putting x is equals to threshold by mean, the equation of average signal to noise ratio is simplified as the mean integral 0 to infinite m x 1 minus exponent minus x m minus 1 exponent minus x d threshold. So the average signal to noise ratio improvement provided by selection diversity is the ratio of average signal to noise ratio when selection diversity is adopted over average signal to noise ratio without selection diversity. So this is equals to summation k1 to m 1 by k, where k is the number of diversity channels. So let us understand this with the help of example. So let us assume there are 4 branch diversities used, where each branch receives an independent Rayleigh fading signal, and if the average signal to noise ratio is 20 dB, so that means mean is given, and determine the probability that the signal to noise ratio will drop below 10 dB. That means threshold is given, that is 10 dB. So compare this with the case of single receiver without diversity. So let us consider when we have adopted the selection diversity, then in that case the probability formula that all these m independent diversity branches will receive the signal less than the threshold is given by PR threshold 1, threshold 2, threshold 3, threshold 4 less than equals to threshold. So this will be equals to 1 minus exponent minus threshold by mean to the power m, where m is 4 and threshold by mean is 0.1. So this turned out to be 0 0.4 times 0 is 82. So when there is no diversity, then the probability will be 1 minus exponent minus threshold by mean. So there is only single branch, so that will be 1 minus exponent minus 0.1, that is 0.095. So if you see both these figures, what we found is that when there is no diversity, then the probability that all these m branches will receive signal less than threshold is more than in the case when the selection diversity is adopted. So thus this means that the selection diversity improves the performance of the received signal. So that is all about the lecture.